Hello. So in this video, let's talk a little bit about more detailed, um, uh, uh, let's say detailed explanations of linear regression. Again, we're going to take the same data set, a small data set here, and we are going to define the predicted y or the estimated y to be the intercept here from the previous example. If you guys remember, this is the model that we got. And from the previous example, this model is going to be used to compute the predicted value y. So this is the actual y, the actual value y, and this would be the predicted value y. So let's take a look at how much would be the predicted value y. The predicted value will be 64.928 plus 0.635 multiplied by this x, and that would be here the predicted value. As you can see over here, the predicted value does not necessarily equal and resembles the actual value. But however, in certain incidents, it may be very close or resemble it to a certain extent. So we are going to find the error, and the error is the actual over here minus the predicted. So that would be the residual error or the errors. As you can see, we have errors in negative, we have errors in positive. In any case, the errors in negative indicates that the actual value is lies above the line. Remember, because if we have here the line and this is an actual value, so this actual value A1, for example, and this is the predicted value, then A1 is greater than P, while the residual that is negative indicates that over here A, let's say it's equal A2, and this is P. As you can see on the y-axis, this P2 is greater than A2, and we always take the actual minus the predicted, so it's going to be in the negative sign. Good. So these are residuals. These are errors because this model only estimates the values. I can just a quick look at the errors. I am really happy with that because I don't have even an error of 1 centimeter. The errors here is less than 1 centimeter. So it's not even a plus minus, a range of plus minus 1. If you really into looking at the behavior of all that, you can take the absolute value of the error, which is something we will consider in the future for a certain analysis, guys. But let's just be able to deeply understand things. So take a look and take the maximum and take the minimum also, or plot it if you want. So the maximum here is less than half a centimeter error. So this is a very good model, I feel. It's a very good model to predict the height of the bébé, of the toddler from 18 to 29 months, because the error is less than half a centimeter. Can't you see that? And let's take a look at the minimum, but we are concerned with the maximum error. A minimum is really a 3-digit. So that's really awesome, isn't it? I think so. Would you like to, just out of curiosity, take a look at the distribution of the errors? Oh, wow, look at the errors. This is the absolute errors, but maybe we would like to take a look at the real errors, like with the signs. So some of them are positive, some of them are negative. Oh, I can see that the errors are totally completely random. They are going everywhere. There's not really a pattern, but let me check. Negative, medium, positive, negative, negative, positive, negative, positive, negative, negative, positive, positive. What do you see here? I don't see any pattern. I don't see negative, positive, negative, positive, negative, positive, negative, positive, negative, positive. That would be dangerous. All right. There is no pattern. There is no negative, positive, or negative, neutral, positive, negative, neutral, positive, negative, neutral, positive. There is no pattern. So that is really interesting. So this is, let's call it residual plot. Yeah. Everything, every step of the way here, it is a very good practice that you plot and take a look and say, is there anything I need to understand or look for in the errors? So something that you really need to look into with the errors is any kind of pattern. If there is a pattern, this means that they are not necessarily normally distributed. If they are random, and these are random errors, negative, there is no pattern, that is good. Especially, this is not really, the pattern is not as of paramount importance as of random. Usually we look into the randomness of the error. But when we are talking about time series analysis, and some of you maybe took statistics too, with time series analysis, we have to look into a certain assumption called autocorrelation if we are doing linear regression on time series analysis, on time series data. So with time series data, we want to make sure that there is no patterns. So meaning that there is no up and down with a certain systematic pattern, all right, or a systematic behavior. Up, down, up, down, up, down, down, up, down, down, up, or something like that. Visually, first of all, you can take a look, and then there are other tests that you can use to detect that mathematically. All right, so now that we are done with this part, let's take a look at another very important error-related assumptions that we want to look into, which is the standard error. Standard error is basically, we always, with the first assumption of linear regression, has nothing to do with the data being normal or the data basically being normal, meaning lies in within two standard deviations. Do you remember? This is the distribution of a normal data. Distribution of a normal data is basically here. Usually we're using a histogram for data distribution. For data distribution, we use histogram. So for data distribution here, we use histogram. And with the histogram, we know that if we standardize the data, then meaning if we standardizing the data is basically taking the difference from the mean, how far is it from the mean, over the standard error. So this will be the mean here, and this will be one standard deviation away, and this will be, and the standard deviation is two ways, positive and negative, and here will be two standard deviations away. Now, and this will be three standard deviations away. These, we don't like them so much because these could actually not, we don't like them so much. But wait a minute, I would like to explain a little bit more. These values over here later, these values over here, we call them mostly outliers. So anything that lies over two standard deviations, we call them outliers. Same applies to errors. Errors has to do with the standard error. If we in data, usually we have standard deviation from the mean. In errors, we don't necessarily take it is call it this way. We call it standard error, which is, this is one standard error, this is two standard errors. So it corresponds to standard deviation, but it's called standard error because the data is not the data, the observed data over here. It's the errors. So you see, it's the same distribution. It's just that this distribution is made up of data that is actually errors, is residuals. So we call it standard error rather than standard deviation. All right. So basically, when you took your course in statistics, you understood that if 95% of the data points, in our case here of errors, if 95% of errors lie in within two standard deviations, then that is really good. This means that we have a normally distributed errors. And then if you have 68% also, it should be lying in within one standard error. All right, let's check our assumption and see if the assumptions are correct. So with linear regression, the fancy thing about it is that, or the usually we check the assumptions before we use the technique. However, in linear regressions, the very first assumptions pertains to the error, and you can't find the error before you actually come up with this line, which is the predicted line. So first you need to create the line, then you need to find the error, and then later on you need to let me just get rid of that for getting rid of the crowd. Then you need to find the error, then you need to make sure that there is a random behavior of the error, then next you need to make sure that the distribution of the error is within the requirement of a normal distribution. How do we find the standard error? You can find it through an Excel function which is a standard, not a standard deviation, but a standard error, which is this function over here, a standard error. ST is a standard, E is error, Y and X. So basically you need to give us the observed or actual or known Y's. These are the height, the known Y's over here. And then you need to get the known X's, which is the guys over here. And that will be the standard error. Now, the two standard error is basically nothing but multiplying this. Oh, sorry, guys. Sorry. Over here, two times this error. Ta-da! So we now need to find out how many, the percentage of points that lie within one standard error and those that lie within two standard errors. As for now, I'm going to use here within one standard error. As you can see, if this absolute value of this error is less than or equal the absolute value of one error, then it lies in within one error. Else, give me 0, because I want to sum up these guys, count these guys, or sum. And the sum these guys for the ones, so I will know how many of these points lie within one standard error. And then the count is basically how many data points I have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But if I have a bigger data set, I'm going to just use the count function, so it will count the number of cells of the range. And then I will find out how many of these values, 7/12, the percentage. Same applies here. I can see that only 58% of the errors lie within one standard error, but 100% of them lie within two standard errors. In this case, I will just be saying standard distance between the observations and the regression line is. Where did I get this from? This is the standard distance, which is over here, the error, and it shouldn't be in percentages actually. I don't know why it's in percentage. So it should be the same. It's in percentage because we're talking about the standard distance between the observations and the regression line. Yeah, it's 0.256 height or 25.6%. That's okay. In any case, we say it's 0.256. This is more natural. I'm sorry for that. So it should be in this format. It's better. All right. So now, as you can see over here, I'm a bit concerned. So because I am a bit concerned, you know why I am a bit concerned. Because anyway, when we put x equals 0, we got the answer that is a little bit deviated away. And probably this is the reason why, because we are 58 from 68 is about 10 points away. 58 to 68, we're supposed to be 68% of the data. So we are like 10% away from our target for nicely normally distributed. But however, there is a tolerance zone. And most importantly, we want to make sure that there is no outliers. So basically, we want to make sure that a very high percentages, which percent of the data, which is 95% of the data, is actually within two standard errors. All right. All right. So we're going to go on with the assumption that because we have 100% of the data point within two standard errors, we are fine, basically, but a little bit concerned that not 68% of the data or more is within one standard error. So we're going to just, in our investigation, mostly focus on the two standard errors. Now let's find the slope. What is the slope? As you can see in linear regression, the slope is basically the coefficient of x. Knowing from the statistics 1, the slope is the coefficient of x. As you can see, this is where we got this the data over here, and the intercept is basically intercept here. If you don't want to plot the data, this is how you're getting your values. So if you don't want to plot the data, or if you want to, if you have multiple linear regression, also you can use this. Also, square r squared. R squared, we didn't talk about it even in the previous video, because the previous video meant to just cover the things that we covered in the previous class. So now it's about time we talk about the r squared. Now, disclaimer, we have two different r squared. We have the r squared, the usual r squared, and then we have something called adjusted r squared, or adjusted r squared. Now, we use the r squared when we have a simple linear regression. Y is equal a or beta 0 plus beta 1 x1. So with the simple linear regression, we use the r squared, or we looking to investigate or interpret the r squared. I'm going to talk about interpretation in a bit. However, when you have multiple linear regression, we use the adjusted r squared because it is been adjusted based on the number of parameters. So when you have the multiple linear regression, meaning you have multiple x's, we need to adjust this r squared take into consideration the number of parameters or the number of x's. So if we have more than x, so basically this r squared or this adjusted r squared will be adjusted for p if p is the parameters, p minus 1, because already we in the base we have 1. So that will be all the extra p's basically other than the x1, because we already have the r squared measuring this part. So we need to adjust for all the extra x's other than x1. I'm going to show you the formula later. So basically, I'm just trying to tell you that the r squared is adjusted based on the parameters, the extra parameters other than x1 in the multiple linear regression model or equation. All right. So now that we have only simple linear regression, we're going to talk about the r squared. And r squared is some researchers and many researchers, especially the older generation, will look into it as a measure of fit. But our generation now, the newer researchers, will not look into it as a measure of fit, of data fit. It's just a measure of how much variation this independent variable explains, the total explained variance that the components of the model, which basically the independent variable here is, we have only one independent variable. So the age as an independent variable is responsible for explaining a total of 98.9% of variance in height, which is not surprising because height is very much dependent on age. But if you are taking other samples, between samples of kids, toddlers has been in a war zone with the male nutrition and so forth, and other kids that been normal. This is under normal assumptions that the kid is nurtured very well, and this is why it is important in your writing your research question, the main research questions that you say that I am attempting to build a model that explains the dependency of height over the age of toddlers at the age of 18 to 29. And if you want, write down toddlers in war zone areas, or toddlers growing in developing countries, or toddlers being nurtured well, normally nurtured by families with versus those that nurtured in an orphan house, for example. So this way you can collect this data on this kind of group, collect this data on this kind of group, and find out the predicted models. So now you can see this is just how much variance this x variable is responsible or explains the variance in the height. So age is responsible in this data set. Age is responsible for explaining 98.9% of variance. In other data sets, you will find out less r squared because maybe the nutrition, the kids are not nutritioned well. So age is not necessarily explaining the 98%, maybe explaining 95%. And then if you as a researcher started looking into other variables, what is different, what's more we can measure, and you ran out another session of data or another term of data collection, and you collected extra variables. For example, you collected variables on their mental health, their nutrition's value, and all that. You will find out probably mental health has nothing to do with height, but you might find out that actually nutrition's, the amount of nutritions they are taking, and the feeding and all that might, or the health of the mother itself and her nutrition may be affecting these babies and so forth. All right. Now, I hope now in this video you were able to understand one of the main assumptions of using linear regression. With linear regression, usually with any technique, in summary, I'm summarizing right now, in summary, with any data analytics or data analysis technique, you usually test the assumptions, then then say I can use this technique, or then you say unfortunately my data doesn't match the assumptions, I cannot use this technique. Or the third option is to clean the data a little, manipulate the data a little, for example, do little transformation, log transformation or whatnot, so you can deal with the data a little and find out if it is now meeting the assumptions. So don't give up immediately, and maybe deal with the data and find out if you can transform, manipulate some of the items, and find out if they are meeting the assumptions, or say basically it's not meeting the assumptions, then I cannot use linear regression, I have to use any other form of regression or any other technique. With the linear regression, however, you need to start with creating the model first. After creating the model, you need to find the residuals. After creating the residuals, you take a look at the first assumption. So this is assumption 1. So the first assumption here is basically the randomness. There is no pattern in the data, and this is very important when we are talking about time series based data. And most likely, and this is a kind of time series data somehow, because it is probably taken over time, every 1 month and so forth. So you want to make sure that there is no patterns in the data, especially with transactional data. Then we're going to talk here about the second assumption. So assumption 2, guys. Assumption 2 here would be the error, the distribution of the error term, not the distribution of the x's. No, not a normal distribution of the x, but rather a normal distribution of the error. Of course, normal distribution takes the form of skewness and kurtosis. We're going to talk about this in a bit. But first, I suggest that you take a look into any outliers. And outliers is any values that lie beyond the 2 standard errors. All right? So you need to find the standard error, and over here there is a function for finding the standard error. As you can see, it is the standard error yx, and you can take multiply it by 2 to find the two standard errors. You want to make sure that you don't have any outliers. However, up to 95% of the data lying in within two standard errors, it may be okay. You don't have to clean the data. All right, good. Now we're gonna go ahead and take a look at how we, instead of using these different functions with Excel just to find the slope or the intercept or the R, and the R, we're going to talk about it in more details in a bit. We are going to use the regression tool, and this will be under data and under data analysis. If you don't have this data analysis on your Excel, watch the next video and we are going to work with it soon. See you in the next video.